In this section, we're going to talk about the units of measurement. The section, along with our next section, is not actually part of Chapter 1. They are part of Math Overview. There are total 3 parts. The third part is something that we're going to discuss at the beginning of Chapter 4. It is called dimensional analysis. And I believe it makes more sense that we discuss dimension analysis at the beginning of Chapter 4, because Chapter 4 is going to use the skills that we discussed from dimension analysis to solve the math problems. All right, what's the unit? Unit is the standard agreed-upon quantity used in our measurements. I just want to point out that any value, a number measured in the science without unit is meaningless. So for example, 10 what? 10 meters? 10 cubic meters? It has to come with a unit. Otherwise, it just leave people to guess. And in our case, it's a millimeter square. And that is a unit of area, as a matter of fact. Well, we are living in a society in this country where we are being exposed by the habit of ignoring units. That is the very bad habit. Now, I can give you an example. What's the price of today's gasoline? And you probably answer somewhere around 180. 180. 180 what? Is 180 or 180? So we're missing unit here. Or somebody could say, oh, it's $1.80 or $1.8. Good. Now we have unit. Is this a price unit? Is this a precise unit for us to describe the price of gasoline? Of course not. It should be $1.80 per gallon of gasoline. So now, as you can see, just how we are being educated to ignore units. That is why doing math and science becomes so difficult to many of you guys. It is not like, okay, so we just cannot do it or something. It's just like we have not been exposed enough with that environment. It's not going to be difficult. Okay, so once you know how to do it, you're probably going to enjoy by doing your math. But I just want to remind you, from this moment on, pay more attention to units than the numbers themselves. It is critical. If you do not pay too much attention to the unit, you better think about taking your career somewhere else, because you're going to have a hard time to pass the chemistry class, because chemistry is a science. Chemistry requires mathematics. It is not the math, the calculation that makes people headache. It's the unit that makes people headache. Because we do not have the habit of this. And then in a very short period of time, we have to train ourselves. We have to convert ourselves to get used to this kind of thing. That is make chemistry so difficult. Of course, the rest of chemistry is not that easy as well. Requires certain degree of memorization, so on and so forth. But the most difficult part is units. And we're going to pick up that topic when we talk about dimensional analysis later on at the beginning of chapter 4. Over the history of human society, and we could have, if not 100,000, but at least we can have tens of thousands units all over the world. We could have hundreds of units for same dimension or physical quantity. For example, mass. As far as I can think about it, we got the grams, we got the kilograms, we got the milligrams, we got the pounds, so on and so forth. And I'm not even started with the Chinese units about the mass. So I just want you guys to realize it's going to be quite difficult for scientists all over the world to communicate their results if we didn't have a set of a standard unit. That is the reason why during 1960s and 70s, scientists all over the world, decided that they are going to set up a international standard units. SI is a French for international standard. And among all these units, there are some base units, which means they cannot be derived. They have to be defined. So the base unit, like units in mass, length, time, temperature, electric current, and the amount of substance. Remember, the base unit for those are not the ones, for some of them, are not the ones that we use commonly in our lab. For example, the base unit of mass is kilogram. kg is an abbreviation for such unit. Why not gram? Because if I'm not mistaken, there's a piece of a metal sealed in a vacuum in Paris, I believe. And that piece of metal made of platinum make it is extremely stable. In other words, the mass is not going to change over 1,000 years because it's also sealed in a vacuum. And the mass of that piece of metal is being defined as 1 kilogram. All the balances, scales in this world is either directly or indirectly calibrated by that piece of metal. So that's the reason why it is a kilogram, the base unit of mass. Same reason, meter is the base unit of length, also known as distance. It's not centimeter or meter because there's another piece of metal whose length is being defined as 1 meter. The base unit of time is second, not surprising. The base unit of temperature is a Kelvin, not Celsius or Fahrenheit. And electric current for its base unit is ampere. And here I'd like to have you guys to notice that we also have another physical quantity, or we call dimension, the amount of substance. The base unit is mole. MOL is abbreviation. Mole actually is kind of like dozen. Right? Dozen is a unit also falling in the category of amount of substance. Dozen means what? 12. Mole means what? That number. Okay, 6.022 times 10 to the 23rd. And that's a sheer number. Why chemistry requires such a sheer number, such a big number? and we're going to have this discussed in chapter 4. All right, so I just want you guys to realize that we have some base unit for these 7 physical quantities, also called as dimensions. As we know, unit is agreed upon quantity, but unit also is special because quantities like values can be added, can be subtracted, they even can be multiplied and divided, but a unit won't do all of it. It only do part of them. Like units can be multiplied and divided, but the units cannot be added or subtracted. Okay. So this is one thing I want you guys to realize. The reason why we called the base units is because that we can derive the units for some other dimensions of physical quantities. For example, force. The base unit of force is Newton, named after Isaac Newton, as you may know. And here we can see, and we can use the units from mass, length, time, play certain combination of these to make Newton, the base unit of a force. There are many forces, but there's one force I like to discuss, which is weight. A lot of people think of weight is the same as mass. In physics, no. Weight is a force. Mass is mass. They have different units. Weight actually is the consequence of mass in a gravitational field. In other words, weight is a gravitational force exerted on mass. Even an object with the same mass could have a different weight when it is in a different gravitational field. So for example, an object that weighs like 300 pounds on Earth would only weigh about 50 pounds on Moon, because the gravitational field on Moon is only 1/6 of that of on Earth. So the force can be changed even though the object keeps the same mass. So that is something that I want you guys to understand. Weight and the mass, although in chemistry class we are allowed to discuss them as like they are the same, but in physics they are totally 2 different concepts. The next common units in chemistry is a volume. The base unit of a volume is cubic meter. That is way too big. Okay, so that is why we have some other common units we use in our laboratory as well as in the hospital. The magical units like a liter, milliliter, in biochem lab, micron liter, μL, or in the hospital, cc, cubic centimeters. All of these are much more common units for volume than the cubic meter. Pressure is the physical quantity we use to describe gas, but it's only in chemistry. But in physics, we have a lot more applications on pressure. The base unit for pressure is Pascal, a unit we named after Blaise Pascal, the French guy who did a systematic study on atmospheric pressure. And he convinced people that the air has pressure at that time. And you can see also we play the combination with the kilogram, meter, and second with the different combination so that we can have the pressure. Pascal is a small for us to use in chemistry. A proper unit would be kilopascal. That means Pascal multiplied by the factor of 1,000. And we have some other common units like ATM, torr, which we will discuss in chapter 10 later on. Another unit, so the dimension is energy, which we're going to talk a lot in chapter 5 in our course. The basic unit, the base unit is joule. Again, I want you guys to notice that still the 3 units, kilogram, meter, second, with a different combination, now we got a joules. So kilograms, meter, second can make a various combinations so that we can have a 3 base unit for 3 different physical dimensions. Joule is small. In chemistry, we prefer to use kilojoules. That means 1,000 times more. And in our diet, we have a calorie. But I'd like to remind you, it is the calorie with the capitalized C, not the one with the small c. The small c, the small calorie actually is dying out or is phasing out. Okay? And start with my generation, and I believe in 2 or more generations, and the calorie probably is going to be out. The last one, okay, I like to introduce here is electrical charge. The base unit is coulomb. Coulomb is too big for the laboratory. And more common units we use in our lab is probably millicoulomb or even smaller, microcoulomb. Mu stands for micro. Even these are way too big for semiconductor industry when we talk about the electric charge carrying through in a computer chip. But they are good enough for us to use in our lab though. So from all the discussion we have here, we realize those base units derived from the unit we defined in the previous slide is either too big or too small. For example, the base unit for volume and electrical charge are too big. The base units of pressure and energy are kind of too small. So that is the reason why you see some letters like C as a centi, M as milli, mu as micro used to adjust the scale of these units. This is something that we're going to discuss in our next slide. If you don't think those units are quite confusing, and we also live in a country that English units are prevailed. So here I'm not going to talk too much about this English unit system. All I want to point out is that we need to memorize how to convert an inch into the centimeters. I just want you guys to memorize 1 inch equals 2.54 centimeters. Later on, if you have to perform dimension analysis, this is the conversion that I won't give you. And of course, I will provide the rest. And since many of you guys I understand are in the health business, I just want to point out there's another conversion that is useful as the conversion between the milliliters to the cubic centimeters, because cubic centimeters is CC stand, or the CC stands for in the hospital. Milliliter is the most common unit of volume we use in the chemistry lab. It is a 1:1 ratio. So 1 milliliter equals to 1 cubic centimeter. So in this class, I want you guys to memorize these two conversions. Now let's talk about the prefix. As we mentioned early on, so we use some letters to adjust the magnitude of the units. So now we realize those prefixes can change the values of a unit by powers of 10. And here's the list of prefixes, from extremely small to extremely large. Pico, a very small prefix, meaning 1/trillionth of its base unit. For example, if we take a meter as a base unit, so 1 picometer is 1/trillionth a meter. And just what substance is small enough for us to use the picometer for its size? Atom. And we got a nano, that means a 1/billionth. In the technology we have now, so we can make particles in the size of nanometers now. Okay. And we got a micron. Micron means 1/millionth. Okay. So if we have something in the scale of, in the neighborhood of a micrometer, that would be the diameter of our hair in that neighborhood. And we have a milliliter, millimeter, milli, we've got a centi and a deci. And from the larger side, we got a kilo, means 1,000 times more. Mega means 1,000,000 times more. And I remember back in like 10 years ago, okay, so we talk about something, the computer CPU in the speed of megabytes. Now we are in the area of gigabytes. And for storage of data, so we can have terabytes. T stands for, okay, so 1/trillion times more. All right. If we use meter, such as how big is a terameter is. Terameter, if I'm not mistaken, is about the size of our galaxy. Not our solar system, galaxy, such as how big this thing is. All right, so with the help of those prefixes, it provides the wide range in the units. What's the purpose of that? The purpose of that is to express very small or very large quantities in what we call a compact way, a way that our audience can understand, can easily pick up that size of value. And let me give you an example. The wavelength of a green light, especially come from the green laser pointer, has such wavelength. It is 0.00000. Am I counting those zeros right? I'm not quite sure, right? So I probably lose count already. 532 meter. That's an extremely small number, because they got so many zeros in front of it. It makes it very difficult to communicate or to represent. So one thing we can do here is try to get help from those prefixes. Maybe you can pick one appropriate prefix to represent such value. So what we can do here is we can move our decimal point around, right? So we can move our decimal point 7 times to the right so that we can have 5.32 times 10 to the negative 7th meter. But 10 to the negative 7th, as we look at these prefixes, we find out it's right in the middle of nano and micro. So which one should we use? In this country, we prefer to use nano. Remember, nano means 10 to the negative 9th. In other words, we're going to replace 10 to the negative 7th with 10 to the negative 9th. If we want to replace 10 to the negative 7th to 10 to the negative 9th, that means this portion, 10 to the negative 9th, is 100 times smaller than its value in order to keep the same value, right? So we have to move our decimal point twice to the right over so that the value should remain the same. Now we talk about the 532 times 10 to the negative 9th meter. Still, it is not that easy to communicate. So we pick 10 to the negative 9th with nano. So we call it as a 532 nanometers. So that is the reason why we developed so many prefixes in SI system. And we should be able to find one particular prefix that is good enough to represent our result in a way that people can follow right away. I would like to have a few words about one important physical quantity called energy. Energy, according to physics, is capacity to do work. The SI unit has been discussed as Joule, named after James Prescott Joule, and we'll soon find out why we name our units after that guy. And here, just how the combination of a kilogram, meter, and second can represent a unit of Joule. And of course, as we discussed earlier, there are more units, okay? So it can have a calorie, calorie with a small c, calorie with a big C, and 1 calorie with the big C actually equals 1,000 times of that small calorie. And that also equals to 4,184 joules. So that is probably why joules is a little bit too small as a unit for us to use in chemistry class and in our diet. The definition of a work according to physics is quite different. The work according to physics is the action of a force through distance, like we shown right here in our diagram. The gentleman here is trying to push this box forward. In order to make this box forward, he has to exert a force to push it. So the force multiplied by the distance the box moves is what we call work. And in chapter 5, we're going to have a much detailed discussion on this. But here, I just want you guys to realize work is one of the 2 major forms of energy transfer that can be used to convert one form of energy to another. Well, from this picture, by doing work, this gentleman, listen carefully, is converting the chemical energy inside his body to the kinetic energy of this box. Because at the very beginning, box does not move. Box does not have energy. And how come it has energy? It has to be some other form of energy be converted from that gentleman, right? So work is a form of energy transfer. Of course, work is an energy, but the work has its characteristics to convert one form of energy to another. And it is one of the two major forms. The other one, of course, is going to be heat. And we're going to discuss both in much more detail in chapter 5 later on. There are many forms of energy. One of the two popular ones are the potential energy and kinetic energy. Potential energy is stored energy or energy due to position. Kinetic energy is the energy of motion. And here, I'd like you guys to take a look at this example to see how one form of energy can be converted to another. We got something sitting on the top of the roof. You understand that's not going to be stable, right? Because it's high, it's going to fall, so make it unstable. Once it's a high, we understand it has high potential energy. Remember, potential energy is energy due to position. The higher the position, the greater the potential energy. Well, this object finally falls down. So as it falls, we realize it loses its potential energy because it's getting closer to the ground. As position gets lower, it loses its potential energy. And the potential energy this object lost is converted to what? Kinetic energy, because we see the motion of this object. So the kinetic energy is converted from the potential energy by what? By the gravitational force, of course. It is that the gravitational force done work on this object in order to convert potential energy to the kinetic energy. So this is just how we can realize, understand the work works. And one other form of energy that is important in chemistry is electrical energy. And from definition, we realize there are two different types of energy. Energy from the position, that would be the potential energy, right? And energy from the movement of charged particle. Movement, that would be kinetic energy, because kinetic energy is energy of motion. And the particle that does or that possess those electrical energy would be the charged particles like ions and electrons in chemistry. And in chapter 2, we're going to have some discussion over these two. Kinetic energy, since it's the energy of motion, which means the faster those particles moves, the greater the kinetic energy it is. But this is not our major concern. Our interest actually lies in the energy stored between this pair of opposite charged particles. Just imagine if we want to hold up these two particles without colliding with each other, that's definitely going to be a force, right? So we're going to have force to hold these two charged particles apart before they collide on each other, having their charge annihilated. So we have to hold them apart. That requires a force. And in order to keep such a distance, there's a work must be done. What kind of energy can be converted to such work? Potential energy. The potential energy actually can be calculated by this equation. This is the law of the Coulomb or Coulomb's law. It tells us just how much energy that is stored in this pair of charged particles. Q plus, the value of a charge in this positive charge particle. Q minus is the value of a charge, or number of a charge of this negative charge particle. R is the distance between the two. That epsilon 0 is some kind of a constant. And that is energy, potential energy, and shows us how this energy can be calculated. And one thing I'd like to point out here is it has negative sign in front of it. So just like between negative 1/2 and the negative 1/3, which one is greater? I want you guys to think of it carefully because there's negative sign in front of it. If we both positive, everybody knows 1/2 is greater. But if we have a negative sign in front of both, it is actually negative 1/3 is greater because it's closer to 0. Right? So from this discussion, we realize the further apart of this particle, the larger they are. The larger they are, the greater the denominator, like 3/2. Remember, negative 1/2, negative 1/3. And the greater the potential energy. And this is the one important statement I want you guys to keep in mind. Because in the third section of this course, we're going to repeat that statement to try to understand the energy levels of the electrons in an atom. Since we talk about chemistry, so there's going to be chemical energy. Okay, remember that is the 5th aspect of the chemistry study. So the chemical energy is the energy stored in the chemical bonds. Okay. And that energy can be released and absorbed in the chemical reaction. So this is what the chapter 5 is going to be. And the chemical energy is a form of a potential energy. Why? Because that is potential energy between the charged particles, electrons versus nucleus, right? So that is potential, that is chemical energy. And we have two fields of chemistry for energy transfer from one form of energy to another, or from chemical energy to a different form of energy. And if we have energy transfer from chemical to electrical, this is what we call electrochemistry. Right now, this field of chemistry is quite hot. I can give you an example. Battery. Okay. I believe many of you guys are old enough to see how big the battery was 10 years ago. Nowadays, battery is very small, and yet it can store much more electricity with such a small size of a battery. So just as this is how this technology evolved in the last 10 years. And the conversion between the chemical energy to heat is what we call the thermochemistry. And the research on thermochemistry is pretty much all over. But we still need to understand the thermochemistry because that could help us to understand the reaction in our research, in chemical research, as well as to understand the chemical reaction or biochemical reaction, okay, that occurred in a different medium. And for all these forms of energies, there's a law for them. We call the laws of conservation of energy. So that means the energy is neither created nor destroyed, but it can change from one form to another. It was discovered by the James Prescott Joule. And that is one of the most important law of energy And we're going to discuss this in chapter 5 and later on in the chapter of Chem 2 class. So that is why we name the energy, the unit of energy, okay, after him, joules. We are living in a country that uses 3 different scales of temperature. We have a Fahrenheit, we have Celsius, we have Kelvin. Kelvin is not common. Kelvin is only common in science, in physics and chemistry. Okay. And what's the story before Fahrenheit, behind Fahrenheit? Okay. Fahrenheit is a name. Okay. And he was a Danish, lived in Britain, and he's the first guy who invented a thermometer. So once he invented a thermometer, he must pick 2 ends to scale the thermometer. So lower end and high end. And for high end, remember that is 200-300 years ago, and people had much less knowledge in science than we do nowadays. So he picked the high end of temperature based on the body temperature of his pet bird. So that is the reason why our body temperature is very close to 100. Less, but close. Because you probably know that already. Bird has much higher metabolism than we do. In order to keep a higher metabolism, higher rate of metabolism, body temperature must be a little bit higher. So that's why it's close to 100 or a little bit over 100 in some of the birds. All right, so that is the high end of temperature. For its low end, 0 degree Fahrenheit, he picked the melting point of salt water he studied at that time. With that scale, water freezes at 32 degrees Fahrenheit, boils at 212 Fahrenheit. And this is the temperature we talk about, okay, in our life. So when we say some temperature is a very pleasant, like 80 degrees, remember 80 degrees is 80 degrees Fahrenheit, so that is the reason why we sometimes are so weak in the units. But in the ears of people from other countries, 80 degrees is a horrible temperature. Because instead of Fahrenheit, they would understand the temperature as 80 degrees of Celsius. So things can get boiled, okay, get hurt with that kind of temperature. Now, the second scale of temperature is a Celsius, named after an Italian guy, I believe he was Italian. 50 years later, okay, or 50 years after the invention of thermometer from Fahrenheit, and this scientist, back then, he was called a philosopher, okay, and he realized that the temperature that Fahrenheit chosen is a little bit odd. Okay, water boils at 332 degrees Fahrenheit, boils at 222 degrees of Fahrenheit. And I want to remind you, back then, that there wasn't any calculator or computer. If you conduct calculation, you had to grab a piece of a paper and start your calculation. And the paper could be very expensive back in the old days. All right, so he decided, let's redefine the scale of temperature to make it easier. And he used water as a reference because he was a scientist and he studied something with water. So water has its boiling point and freezing point, right? So he said 0 degree for the boiling point, no, the melting point of water, which is the freezing point of water, and 100 degrees for the boiling point of water. And that make calculation a lot easier. So that is why even nowadays we still use the Celsius. That scale of a temperature was good for about 150 years. Later on, the temperature, this scale of temperature now has made a challenge for a very special field of physics. It is called low temperature physics. When we talk about the low temperature, that is almost negative 200 degrees of Celsius. Remember, it's become quite difficult to communicate to people with a temperature that is always negative. Okay, because, for example, negative 200 degrees, negative 100 degrees, which one has a higher temperature, right? So people have to think about it, okay, before realizing it. And research also shows there's a limit of a temperature. That means temperature cannot go any lower. That the bottom line of temperature is a negative 237, no, I'm sorry, negative 273.15 degrees Celsius. Once people realize that, scientists proposed the third scale of temperature, which is Kelvin. That is a unit for SI system. And it has a 0 degree Kelvin, which is absolute 0 degree. That means nothing can go beyond absolute 0 degree Kelvin. What is good about a Kelvin is that a Kelvin has the same size degree as a Celsius. That means 1 degree difference in Kelvin is exactly 1 degree difference in Celsius. Okay, according to this new scale of temperature, now water freezes at 273.15 Kelvin, boils at 373.15 Kelvin. Again, we're talking about the temperature of water in some numbers that is not convenient for us to calculate. So that is the reason why we still use the Celsius for the study of solid and liquid, except for something in the low temperature though. And we use the Kelvin in chemistry for gas and energy calculation. Temperature is very closely related with the heat, or vice versa. In order to differentiate these two, and we must understand the definition of temperature is a measurement of how hot or cold a substance is related to another substance. And we're going to talk about this a little bit more later on in chapter 10. Temperature is an intensive property. Why? Because temperature is independent of the size of the subject. For example, if you have a temperature of 100 degrees Celsius, water, regardless the size, or regardless the volume, or regardless the mass or amount, will boil. Make sense? So temperature is an intensive property. And since we're living in the country that uses the 3 different scales of temperature. So here I'll provide you the conversions of 3 scales of temperature. And I do not expect you guys to memorize both of these conversions, just to memorize one set of conversions. For example, Kelvin to Celsius, Fahrenheit to Celsius. So just this one set, for example, and then you can automatically derive the second set using math. Heat, on the other hand, is energy flow between objects at a different temperature. Heat, however, is an extensive property. And you probably recognize, in order to keep the ice water long enough in low temperature, we need a lot of ice cubes. Make sense? Because it depends on the size or the amount of ice cubes to keep temperature low enough. So heat is an extensive property. And that is pretty much all for this section, okay, of lecture, because here we just focus on the units of a measurement, and we discussed some important physical dimensions like energy and temperature. And we discussed the units of these physical dimensions. And also, I want you guys to realize kilograms is the base unit for mass. Meter is the base unit for length in the SI system. Okay, even though they are not a common unit we use in our lab, but this is how they are defined in the science. And that's it for this section. And I thank you for your time. I see you guys in the next section of discussion and lecture.